That's not bad.
What does it mean by? I don't know what this test is testing about, but Asam has studied it for like a while.
I mean, I'm not far for you.
Stuck in there.
Yeah.
So this looks like you're returning -1 for most similar word. You should never be returning. No, it says the similarity is considered to be minus. So if the word is if you can't compute the similarity, it's considered to be -1. So if the target word is not in the vocabulary, then all the similarities are -1. It's a tie, and you return the first word. But it's the similarity that's considered to be -1. It's not what this is returning. This always returns the word no matter what.
Always return the word.
Yes, that's what it said. Yeah.
Okay, but like if it's -1,
The
then what?
similarity, no, the similarity is considered to be -1. So there's two situations. So one is the target word is not in the vocabulary, in which case all the similarities are -1. And in case of a tie, what it says is you return the last row of children. The other situation is one of the choices is not in the vocabulary, in which case, well, for that one, the similarity is considered to be -1. Yeah. All right. So I think it might be hello. So I think it might be that not everyone is here yet. So just for the people who are here, and maybe I'll repeat it. So there is one more quiz, and basically we're please, at least, like, if you have a lot to say about how awesome this course is, you don't have to finish the evaluation, but please start the evaluation for ESC180. If you can finish, that's great as well. You can press OK and finish later, but better yet, finish it now. The course evaluations, course feedback are important, both because I want to know what went wrong, what went right, so that they can improve this year. Also because it's my job. My management looks at the course evaluations and decides whether to keep me around, whether to give me a raise, stuff like that. Yeah, that as well. Yeah, thank you. Yeah, if you would, it would be helpful if you gave your feedback. Thank you. I always feel like an Uber driver asking for a rating. Right. I don't take tips. So I'll give you a few minutes to kind of fill out the evaluation. Press the OK button. As promised, so the tournament for Pong is going to be, after the semester ends. So you have until Wednesday plus grace days, I suppose. If I don't suggest that you use them, but you can if you want, to submit the Pong for the tournament. I do encourage you to try it out if you have the time today, tomorrow. I think you're done with everything else. It doesn't take all that much at all to beat the chaser. All you need to do is install Pygame. There's instructions on the Pong website how to do that. And you just need to do something a little bit cleverer than just chasing the ball. It's really not difficult, and you get half a point towards your course mark. And I think it's good practice. I encourage you to do that. The tournament, of course, whoever wins. So I kind of randomly picked Arya and Chandresh's submission and Boya's submission. So Arya and Chandresh are going to be on the left. Boya is going to be on the right, and we'll see how it goes. Fill out the evaluation or watch the Pong. You can multitask. I did not run it ahead of time, so I don't know how it's going to go. Of course, it goes differently every time as well. Yeah, so this is just two random submissions. I did not run any, seed tournament or any. Wow. All right. Okay. Rematch. Okay, please fill out the evals. We'll play one more game while you're filling out the evaluations. So they switched sides now, so it's so Boya scored, I guess. Yeah. Oh well. So are any of you here? So Arya Chandresh here? No? Boya? All right. Well, maybe you're watching on video. No, that's close. That is how I lost yesterday to a lot of people. Yeah, it accelerates every turn. Yeah. All right, that's interesting. Yes, I just made it accelerate kind of every time a point is scored, it's faster because otherwise it never ends. All right. If you're watching on video, congratulations. But that was just an unofficial match. The tournament's gonna happen after the semester. The prizes as promised. Again, anyone can do it. Just to beat the chaser is just not difficult. Yes.
Sorry, what is it do again?
So it's due Wednesday midnight, but I guess it's an assignment. So if you use your grace days, I can't stop you. But they don't recommend that you do that. Yes. I mean, it's not like it's going to be offline. So because like it takes a long time because like you saw, like here it was like up to 10, it's kind of up to chance. Of course, in actual tournaments, it's also a bit up to chance, but I like to run it for a long time so that it's like definitely the best player wins. So I run it like overnight offline and then I announce the results and then there's going to be like a demonstration game between like the gold medalist and the silver medalist. All right. Okay. So people who came in late, please start writing the course feedback on Quirkus at least. Maybe finish it. Say okay. You got your quiz 12 mark. Okay. So a few quick things. So yesterday on Discord, people convinced me kind of to release the tests that we're using on Gradescope currently for Project 3. It's a bit of a balancing act because I really do think that it's a little bit artificial if you know the tests. It's better if you write them yourselves. At the same time, people were asking so nicely. So I decided to release them. I think, what is good is that they're kind of in a weird format. There is a way to run them on Paizo. So if you look at this video, there is a demonstration of how to run the tests in Paizo and to debug them, tracing line by line. So that was my justification for doing it. If you come to office hours, which there's going to be, there is today, later in the evening, there is also going to be tomorrow and Wednesday. I will ask that if you are asking about the tests, that you first follow the instructions in the video and you show me that you at least tried to go step by step, put a breakpoint where you think the test is going to fail and look it up. I think if you follow it, it's a learning curve as we made you do it in the lab, maybe in a less complicated scenario. But it's a little bit of a learning curve, but not that much. Like you can learn to do it in 15 minutes and it stops being annoying. It starts being very fast. So just do it now, might as well. So Samantha is doing a course review session on Zoom. If you feel like you need extra help as well, you can get in touch with Samantha. I will also have office hours, so you have a choice about what to do. That is answered. So we had a good turnout for ping pong. I think I lost most of the games, but that's fine. I rounded up and I donated $42 plus transaction fees to the Humane Society. So good for the dogs. I will after this go and play football with whoever wants to play football with me in the common room, if you don't mind being VTFO'd. So, okay. So, that's that. And what I want to do now is do one last thing for this course, which is hopefully to give another example of a substantive use of recursion. We already had one, we had several where you could do it with a loop, and that's merge sort. So that's basically the sort that's built into Python. But first, I want to review complexity of recursive functions. So this is in the notes here. So here's the kind of thing so this is in the notes linked from the calendar, right? So this is the kind of thing that we've done up to now. So if you have a factorial function, assuming that every call meaning every computation that's like this, basically, takes the same amount of time, what do you need to know about the complexity? Well, you just need to know how many calls there were. How do you know how many calls there were? Well, you just say, well, we start with factorial of n, and then we call factorial n minus 1, and so on, up to factorial of 0. How many calls is that in total? N plus 1, because 0 to n plus 1 calls. So if every call takes the same amount of time, then the runtime is going to be proportional to n. Make sense? So does anyone see, by the way, a problem with this logic anywhere? Yeah. Yeah. So, well, it depends a little bit. So if n is an integer, integers in Python are not limited, which means that you're computing products of huge numbers very fast when you're computing factorials, right? However, if n is a float, so, and on the exam, you'll notice that everything is a float because I worry about this, then it's not a problem, right? So for floats, multiplication takes the same amount of time. We're not on the exam for ESC180 worried about what happens with integers. Questions are worded in such a way that this is the right answer. Make sense? Fun fact, if you ask ChatGPT, at least as of a few weeks ago, what's the complexity of this and explain why it is not O of n, ChatGPT says, no, what you're talking about, Jude, it's O of n. And because of that, they put this question saying, if n is an integer, what happens on the TA application, and said, well, this is what ChatGPT says. Why is it wrong? And then I basically hired the people who answered correctly. A lot of people were like, no, dude, it's definitely all of n. ChatGPT is right, you're wrong. And I was like, it's good, it shows independent thinking, but also, yeah. Anyway, so, okay. So here's the example from, that was just a fun story. If n is a float, like it would be on the exam, it's O of n. Yes. O of n and O of n plus 1 are mathematically the same. And so the simplest form is O of n. For large n, the ratio between n and n plus 1 is just 1. Sorry, so that's so the question is, why is the integer and float thing different? And the answer is, the key thing here is to know whether this takes the same amount of time every time or different amounts of time depending on what n is. So because integers are unlimited in size, multiplication of very large integers would actually take longer. So this logic of just count how many calls would not work. But that was like an aside. Okay, so basically on the exam, it's going to be a float. When it's a float, multiplication, addition, any arithmetic operation takes the same amount of time every time. The answer is O of n. You could also say mathematically it's O of n plus 1 too. It's just that you're asked for the simplest form. And the simplest one is O of n. Make sense? All right, so stochastic exponentiation. So that's the thing that we were just done with last time, right? And the idea is you compute, so here I kind of simplified it and didn't worry about the situation where n could be odd. So this is the simplified version. The good one is from last time. So we're saying compute the half power, so basically x to the n over 2, and then return half power times half power. So if n is a power of 2, that's going to work. All right. So what's the complexity of that? Again, you draw the call tree like we had done last time, right? So first you have a call to n, and then that calls power n over 2. So there's a call to n over 2. and then there is a call to n over 4, and so on up to 0. How many calls in total in this call tree? If you go n over 2, n over 4, and so on down to 0, that's log to n plus 1. Right? And the logic is, again, that's what log means. We had several examples like that. So that's log to n plus 1 approximately calls. So that's all of log n. This sounds like a lot. The point of this web page is to say there aren't very many of those trees that you can draw. So I'm telling you about like 4 of them right now, and those 4 are basically everything that you are going to see on past exams. So it's kind of a lot, but also kind of not a lot. Okay, questions about this? Is this good? There's discussion in row 2. You got the good seats, guys. You got your money's worth. Okay. So, guys, 29 more minutes, and then you can talk all you want. All right. For a while. So here is another example that we can think of. So let's say that I want to compute 2 to the n. And the way I will compute 2 to the n is like this. So I'm saying 2 to the n minus 1 plus 2 to the n minus 1 is equal to 2 to the n. Right? So that's the recursive step. Does that make sense? Questions about this? So all this is saying is 2 to the n is equal to 2 to the n minus 1 plus 2 to the n minus 1. That's mathematically true. So that means I can use it if I have a base case, which I do. Make sense? Okay. So what is that going to look like? So I'm calling slow power to n, and that makes 2 calls. So once to compute 2 to the n minus 1, and another time to also compute 2 to the n minus 1. Does that make sense? So 2 to the n minus 1 also makes 2 calls. 2 to the n minus 2 plus 2 to the n minus 2. And it does the same thing over here as well. And then every one of those also makes 2 calls. So how many calls in total do we have? So the trick here is to look at this tree and count up the number of calls by levels. So we have 1 call here on this level, and we have 2 calls here on this level. How many on this level? Yeah. Who can count to 4? Okay. Okay. Now it's more difficult because you can't count. How many calls on the level after 4? 8. 8, because every one of those spawns 2. So it's 2 times however many there are here. Make sense? Does the overall logic make sense? So I'm looking at this function. I'm saying I want to draw the call tree. Right? So this is the call tree where n calls n minus 1 twice and so on. And then I need to somehow count up how many calls there are. And the trick here is to say, I'm going to count up level by level. So it's going to be 1 and 2 and 4 and 8 and so on. And eventually I'll get to here. Not going to say what this is yet. Okay. So what is it though? Well, I can say, well, 1 is actually 2 to the 0. and 2 is actually 2 to the 1, and 4 is actually 2 to the 2. And how many levels are there here? If I go from n to 0, how many levels is that? N plus 1, that's right. So what is this? It's 2 to the n, right? Because I go like 0, 1, 2, and there's n plus 1 levels. So it must be that the last one is 2 to the n. There's other ways to get at that as well. So now what I got to ask is how many cols in total? Well, sum up the number of cols on every level. So that's going to be 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the n. And this is the other formula in addition to arithmetic progression, that the arithmetic series that I want you to memorize. This is 2 to the power of n plus 1 minus 1 divided by 2 minus 1, which is equal to 1, which is approximately 2 to the power of n plus 1, approximately in the sense that it's that minus 1, which is equal to 2 times 2 to the power of n. So it's O of 2 to the n, assuming every col takes the same amount of time. Yes. No, so arithmetic series and geometric series, if you're not doing anything tonight, please memorize those. Good a time as any. Yeah, like I like literally for that reason is that, you know, at some point you got to know this. So I'm deciding that this is the point. All right. One thing I would do when I was in undergrad, which maybe was not good for long-term retention, however, worked out for me, as you see, I remember it now, is on the subway on the way to the exam, I would just like memorize whatever it is that I need to know. And then like the first thing that would happen when the exam would open up, I would just like write everything down. So, you know, that is allowed. You're allowed to use the cheat sheet in your head. Okay. All right. So does this make sense? Does this make sense? So this is O of 2 to the n, which is why it's called slow power 2. So here's another example. So this is the sum list that we had last time as well, right? So the trick here to remind you is in order to sum up the list, we sum up the first half, and then we sum up the second half, and then we add those. Questions about this? Is this good? Okay. So what's the col tree over here? So we start, so the square brackets here is because it's a list of size n. It's not like the number n. We start with a list of size n. And then we make two cols to sum up this half and to sum up this half. And in order to sum up the left half, we need to sum up the first half of that plus the second half of that. Okay. So that's the col tree. So now, again, how many cols? This is a little bit tricky and kind of funny when you look at it. So this is 1, this is 2. It's the same pattern as before. But the difference is there's a lot fewer levels. So we're trying to say how many cols in total. We want to sum up the number of cols on every level of the tree. And it is, again, 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus and so on plus 2 to the what? Anyone? How many levels are there here? We go from n to n over 2 to n over 4 to n over 8 and so on. How many levels is that? That's the same thing as we, well, you know, someone else. Yeah. How many levels? Anyone? Who says 2 to the n levels? Okay. Who says n levels? Who says log n levels? You're correct. Okay. So, well, log n plus 1. So why is that? Well, because we are going from n to n over 2 to n over 4 to n over 8. So think about how long do we need to go along this branch to get to the 1? We divide by 2 every time. That's exactly log 2n. Does that make sense? Does this not make sense to anyone? Okay, so we have log 2n levels. So that means that the last thing here is 2 to the power of log 2n. Make sense? So how much is this? Well, same formula. So this equals to 2 to the power of log 2n plus 1 minus 1 divided by 2 minus 1. So that equals to 2 to the power of log 2n plus 1 equals to 2 times 2 to the power of log 2n, which is, so 2 to the power log 2n, so power and log cancel each other out. So that's just 2n. So the unit here is cols, so this is ohm. Make sense? Yeah. Yeah, well, so again, the so just one, so this is just the arithmetic series, right? So r to the 0 plus r to the 1 plus r to the 2 plus r to the k is equal to r to the k plus 1 minus 1 divided by 1 minus r. This is called the geometric series. Make sense? Okay. Yeah. So we don't drop it. So this is 2n, but that's proportional to n, right? So when we write the simplest possible form here, we could write 2n, but that's not the simplest possible form. 2n and n are just proportional. Does that make sense? All right. Questions? Okay, is this good? So this is kind of remarkable, right? Because this tree kind of looks like it branches out. But the thing is, it branches out, but it doesn't branch out fast enough because there's just log 2n levels. So it cashes out to being proportional to n anyway. Yeah, there's a question somewhere? Yeah. Okay. So this is some list. I'm going to skip this right now. If you're interested in the details of this, you can look it up, but there's no time this semester. So I guess you'll hear about those particular details in 190. And I want to go to merge sort. So here I have 15 minutes. That should be okay. So here is the basic idea of merge sort. It's kind of like the idea behind some list. So if I have a list, whatever, that's not sorted. What I want to do with it is I want to split it in half. I want to sort the first half and I want to sort the second half. And then I want to get the result. Right? All right. So it's kind of like sum of the list is like the sum of the first half plus the sum of the second half. Add those up. Same idea. So I'll just show you what that's going to look like. So we make the call here. And we make the call here. And then this guy, if we sort it, that's going to be, you know, this we can do by eye. And you can kind of see that if the list is shorter, you can do it by eye. Make sense? And then if the left half is sorted and the right half is sorted, you can kind of see how you would take the two sorted lists and kind of interleave them so that they are merged. Right? So how would that go? You would say, okay, so I'll take this two and I'll take this two. And then I'll take, I guess, the 5, 6, 10. And then I'll take 123 and 5, 6, 7, and I'm done. So that's the idea, right? So split the input in half, sort the first half, sort the second half, merge the results. Done. Yeah. I'm about to do that. Okay. So, but first I'll write the code. So same as sum list, right? So sort the first half, sort the second half, merge. All right. So that's the recursive step. Right? So same as sum list, except sort the first half, sort the second half, merge them together. Does this make sense as a recursive step? Like if you can do merge, of course. All right. What's the base case? If you want to sort a list, what's an easy list to sort? Anyone? Yeah. Yeah, exactly. So what's the output? Like it's already sorted, right? So just return a copy. Does that make sense as a base case? Like if the list is of length 0 or of length 1, it's already sorted. Don't need to do anything. Just make a copy and return. There are, in fact, 10 minutes remaining. Make sense? Okay. So that's it. That's merge sort. That's the magic of recursion, right? If you have the right recursive step, it doesn't take that long. The only thing is we haven't written the merge function yet. So to your question. Oh, yeah.
Why do we return a call?
The question is, why do we need to return a copy? And the answer is, if it's a function that's returning a list, you don't want to sometimes return something that's not an alias and sometimes just return an alias of the input, because the user of the function would not know that sometimes you're returning the alias, so that might mess things up. Does that make sense? Okay. So merge. Like basically, and L1 and L2 are sorted. Okay. And you could, of course, say, return sorted L1 plus L2, but that's kind of cheating, and that would be slow because it's not using the fact that L1 and L2 are sorted. So rather what we'll do is we'll go through both lists and just say, well, like which one is the smaller, just put it in the result. So I1 and I2 are tracking where we are in L1 and L2. Say while 1 is smaller than length of L1, and also I2 is smaller than length of L2. Right? So what we're doing is we're basically like advancing in the left half of the list and in the right half of the list, and putting the smaller element into L1, into result. Is that making sense? Questions? Okay. So now that we're done, we exhausted either L1 or L2. But we don't care. We'll just extend result with the rest of L1 and also the rest of L2. One of those is going to be empty because the reason we stopped the loop is either we ran out of elements from L1 or we ran out of elements from L2. Does that make sense? Questions about this? Yeah.
L1 and L2, they are like in and of themselves sorted lists.
Yes. And that's why we got to say, like, I'm going and saying, well, like, we've got the 2 from here and the 2 from here. And then, well, like the smaller, so that's 5, the smaller, so that's 6, the smaller, so that's 10. And now we ran out of elements from L1, so we'll extend with the rest of the elements from L2.
But if we're using merge sort, don't all the lists in again.
We are not using anything. This is just a function.
So we're gonna.
Well, we already have, right? So we called merge from here. Yeah. Make sense? All right. This is obviously not on the exam, so I'm gonna run through it in a couple of minutes just so that you see it. but like the last 15 minutes of this course are. Apparently not on the 180 exam, might be on the 190 exam though. I'll have to like repeat it. All right. So that's the whole of merge sort. Make sense? Now that they said that it's not on the exam, it's got to make sense. All right, just this part. Okay, so for the record, 15 minutes, I mean, like starting from when I started talking about merge sorts, not on the exam, but nevertheless, in 4 minutes, I'm going to give you a preview of what that looks like. So what we're going to say is, okay, so this is one loop. So this runs in time that's proportional to the length of L1 plus L2. Make sense? And then the trick is the call tree for merge sort. So this is merge sort. The call tree for merge sort is the same as the call tree for sum list. Right? It's like this. The thing is, though, that the calls now don't take the same amount of time every time. The calls are proportional to the size of the input because merge is linear time. But we can still use the levels trick. So we can say, on the whole, this level takes time that's proportional to n. And on the whole, this level takes time that's proportional to n over 2 plus n over 2, so also n. And on the whole, this takes time that's proportional to n over 4 plus n over 4 plus n over 4 plus n over 4, so also proportional to n. How many levels and tolls? Log to n. So that is how merge sort is all of n log n. Which is kind of remarkable. You would not think that you would have a kind of a formula like that just pops out, but it does. Merge sort is the sorting function basically that Python uses. It's a little bit more complicated for smaller lists. It basically, like it is merge sort, but if the length is smaller than 10, it switches to a different sort because it turns out to be faster. It's called Tim sort, so the name is on the slides. You can look that up. All right. Last questions. Okay. So I think that's about it. I want to thank everyone. I want to thank you, the people who came here, the people who are watching, the people who will be watching on December 13th. Thank you as well. We have the TA team. So Youssef never got around to sending me his photo. However, I did happen to talk to him on Zoom. So that's Youssef. So Professor David James was sitting in over there, was sitting in on the lectures, give me advice. And thank you very much for the demonstration, which I think a lot of people were excited about. That's great. Thank you very much, Professor James. And thank you. This is not goodbye. I will play football with whoever wants to challenge me. Don't try me. I'm going to the common room, and otherwise there's going to be office 190. But yeah, see ya. Thank you very much. Bye. Hey, have a good night. Bye.